Start my real talk, I'd like to do a demonstration. One of the recent new features, well, let me first introduce myself. For those who don't know, I'm the author of GHCGS, and well, that's my way of solving the JavaScript problem, but more on that later. One of the new features of GHCGS, and one of the most requested ones, is a REPL called GHCJSI, since, well, pretty hard to pronounce, but that's pretty much the only thing I could think of. It's in an experimental branch in the GHCGS repo, and you can play with it, but it's not quite ready to merge into the master branch. But still, it's quite fun. So let me show how it works. No, I should restart this. This is a bit too small, I think. Basically, if you know GHCI, then you can run this thing. Well, I don't have a wrapper executable, so I have to write it out completely. It also works with Cabal REPL. So if I start the REPL, can everyone read this? I can make it even bigger, but it's just what you get. It says GHCJSI and then longer version number rather than GHCI. If I type any Haskell expression, like whatever, then the first time it takes a while, it compiles the expression to JavaScript. It collects all the dependencies of the expression, and in this case, it compiles the expression to something that prints the result of this pure thing. So it collects the dependencies, which is basically the GHCDS runtime and the parts of the base library that have to do with dealing these with numbers. I think it defaults to integer, and with printing all these things, so all the character encoding stuff. So this takes some time the first time, but at the moment, this all the code that I evaluate is running on a Node.js thing in the background, invisible. The second expression, if I can do the same things as in GHCI, so I can do bindings. And I can inspect the type. So it is polymorphic, so I can print it, for example, as a double. And now it's much faster. So it compiled the expression, but it remembered what was already on the JavaScript runtime, the Node.js backend process. It only collected the additional dependencies for my new expression, sent those over, gave it the command to run, and collected the output, the standard output or the standard error output from the JavaScript process back. And so it just feels like GHCI REPL, and that's pretty much how you use it. Well, now I have to restart it since there's something not quite fully finished, but it gets more interesting since we do have JavaScript. In this session, I have access to the whole Node.js environment, so I can use the foreign import JavaScript extension that GHCGS adds over to GHC actually, but in GHC itself it's not supported. But it's, the interesting thing about JavaScript is that you can run it in a browser. So if I restart GHCJS, and I have to go to this and connect to port 6400 on localhost, then my browser has connected. So the browser connects with a WebSocket connection to the Node.js backend server. That was the easiest way I could get it to work. I might still change the architecture. But now when I enter an expression, the Haskell runtime is sent over the WebSocket connection to the browser, and there it runs. So if I type some, yes? Well, this browser is Safari, so it just runs JavaScript core. And JavaScript core is actually faster for most GHCDS code than V8. But in the browser, I have the document, I have the window, I can interact with it, that kind of thing. So that's more fun. I can still do the same thing as I just did, so it remembers. This thing takes a bit longer now. This is it's not quite finished. So there are some things that aren't quite ready. So sometimes the browser or the standard out from the backend process is interleaved wrongly with the command prompt. Those things all need to be solved. That's the reason it's all not merged yet. But anyway, this thing runs in the browser now. It should print 55 after a while. I claimed that JavaScript core was faster. I hope I'm right. Currently it's not. So I hope I didn't do something wrong. Oh wait, yeah, I should have remembered that. Safari, for some reason, suspends the JavaScript execution if you don't have the window in the foreground, and I think it's battery saving or something. So I had to switch to that. Yeah, it does work. Printing numbers or just interacting with the session that's now running in the browser JavaScript engine is not really making full use of the browser's capabilities. So I have a demo file loaded with lots of things. Among those, a function called table, which has some uses some Java foreign functions to talk to the browser about the documents, adds a table to the body of showable things. So if I do something like map, I'll do something like then that's a typo. Thanks, Haskell. So, now I have something in the browser. GHCJSI runs in the browser, but it has no specific support for dealing with expressions, or it's not an interactive worksheet or whatever. You just have access to the browser, but you can do very interesting things with this. Now I have some cruft in there, so for my next result I might want to clean it up. I have a clear body. Thanks for the completion here. All the JS underscore things are the foreign JavaScript imported things that allow me to do something. But I have something more fun. I have a backend for the Gloss library that draws on a HTML5 canvas. Gloss is a library by Ben Dipmeyer that normally works with OpenGL to makes it really easy to write animations, interactive games, very simple, and it's really fun to play with. And this makes it even more fun to play with. So I have a mostly complete, but not quite, backend for GHCDS, and I added some utility function that just does a bit of setup work to run an animation in the browser. So I have also a few things. I think square is right. So now I have a square, but the square should be inside the black square, but it's also black probably. So that's important. So all the normal GHCI functions work. It's just the whole session copied, and the one thing that I changed is the code generator and the linker. Instead of the bytecode linker that GHCI uses, this uses the GHCGS code generator, and that has its own built-in linker that has a linking method that's similar to split objects in GHC. So it can in a fairly fine-grained way collect the dependencies of an expression and in this case, send them incrementally to the browser. But if you statically link a program, then you get a separate JavaScript file. So I built this in approximately a week last summer because I basically already had all the ingredients. I just needed to copy the session code, the GHCI session code, and change the GHCGS code generator a tiny bit to work with this. Let me see if I can make it work better, or if we can actually see something. Make it red, and then the square again. Yes, so now it's actually a visible square. Still not very impressive, but let me explain how this works. When I start the animate action, which is just an I/O action, I can pull up the source code for that. I hope I have it here, and that's probably very small. But those in the front, it's something there's no specific GHCDSI support for this. This just uses all standard Haskell constructs. It's a bracket of clearing the body and finally clearing the body again, and then running the underlying gloss animation thing. So when I press Ctrl-C in my REPL, it throws an exception to the currently running, foreground running I/O action. As long as it's not returned, then it does that, which, well, triggers the exception handler here. That removes the canvas element again, and then my document is blank when and my REPL returns to the prompt. I can also fork I/O things in the background, so I can do animations. I can start an FRP thing that works, and then if I fork I/O this thing, then I just get my prompt back immediately, and I can interact with it through whatever I have, say I/O refs that I can modify, or events that I push through. So there's no specific support. You just do Haskell and concurrent Haskell like you used to. You just throw exceptions to threads to kill them, and that's how it works. So if I press Ctrl-C here, then this thing disappears, and I can do things like, well, I can make a rotating square, for example, since gloss is animations, still simple. I have something like, well, this. So now I have a bunch of rotating squares. I can make that rotating again. Let's see if this works. And have some snazzy zoom. I think it's called this. Yay. So very fun. And well, I just want to show it off. It's probably going to be merged later this year, but the problem is that the code for the GHCI session is not part of the GHC library. I have a whole bunch of copy-pasted code in my in the GHCDS repo, at least in the experimental branch, and I'd like to make it a bit cleaner, make the cleaning up all these tasks a bit neater. If you connect the browser after you've evaluated an expression, then the new Haskell expressions are sent to the browser, but everything else is still on Node.js, so the Haskell runtime is not complete there. It's all these things that are not quite there yet, but well, it's a start, and a fun start, I think. So these are the things that I like. But let's go back to what I was actually going to do here and try to solve the JavaScript problem. That should be here, and I have slides. And perhaps this too. So the problem is, as everyone knows, but this is all slide. Well, everyone knows JavaScript is everywhere. It's dynamically typed. It has not particularly been well designed. I think it's been designed in a weekend or something, and we're still dealing with the consequences, since basically it's the only thing that we have on the web. And yeah, if you have small JavaScript programs, well, that works, but the bigger they get, the harder they are to maintain. So we don't really like to write JavaScript. But, well, we're sort of stuck with it. The solution is, obviously, to not write JavaScript. But, yeah, we still want to make these applications work. Well, my solution, or at least the GHCDS solution is, and it's hardly unique in this domain, is to take some other language that we prefer, or for some reason, and compile it to JavaScript. And we have a whole bunch of other languages. In the Haskell area, we have also Elm and PureScript, which are both inspired by Haskell and functional and statically typed. There are also in other areas many languages. So many even that JavaScript has been, or there have been things in the design of JavaScript that have been influenced by using JavaScript as a compile target rather than a language that you compile directly in. So I have a whole bunch of things that are already in the language or are some specification part of the language. SMGS is a subset of JavaScript that can be compiled really efficiently for in Firefox. They have adapted their engine to that, but it's still the source code is still JavaScript. There's also WebAssembly that tries to take this to the next level, and instead of JavaScript source code has a binary intermediate bytecode format to save the step of parsing these things. The ECMAScript 6, which is called ECMAScript 2015, which was finalized this summer, has some new features that have been specifically added for these SMGS and WebAssembly things. Like there's a new integer multiplications thing. JavaScript numbers are all floating point numbers, but there's this new integer multiplication, since multiplying two integers with the existing JavaScript numbers is really inefficient. And there's also other things like ES 2015. No engine unfortunately implements it yet, but it has support for tail calls. So the specification identifies a few positions in the source code that are tail positions, and if you call a function at those positions, the JavaScript engine is not allowed to grow the call stack, so you can call in infinitely deep into functions. That's really useful for, well, some functional programming style, but also for using JavaScript as a compile target. And something else that's in particular useful for Haskell is that Haskell supports all kinds of weak references and tricky memory management things that require you to know something about which values are still reachable, and if you want to do things like is my thread deadlocked, or is my am I waiting on an mvar that's never going to be updated again, you need to know a bit more of what values are in scope, and current JavaScript doesn't really give you that. Future version of JavaScript will give you that. That's more or less the problem we're facing as compiler developers. We try to make our code as good as possible, but unfortunately all these new features are not supported everywhere. So the current project for GHCGS is to make as much use as new features as they become available, but make them optional, since we can't really expect everyone to have a JavaScript engine that has all these new features immediately. Like people still ask for IE8 support, and well, that's pretty painful already. But anyway, once we have another language that we compile to JavaScript, we still have to deal with this environment. Sorry about that. Can you hear me? Is it worse? Okay, good. So the thing is, we have this environment that has been designed for JavaScript, and all the interaction with, say, the browser document, eventually it will have to go through some layer of JavaScript. So we can abstract away much of that, but in the end, especially for GHCDS, which is relatively early in development, there are not too many libraries. There are many JavaScript libraries that people probably want to use. So there's going to be a point that you are going to have to talk at the JavaScript layer. So that's the secondary problem. And well, that's basically the topic of the talk. I'm going to give you an introduction first on the status of the GHCDS project, and after that something on how we deal with basically two particular problems in dealing with the underlying JavaScript environments. And one is the foreign function interface dealing with calling JavaScript, passing data from and to the Haskell land, and the other is concurrency. How do we deal with our Haskell threads, and how do we map them to the environment in the browser where we have event handling and asynchronous JavaScript code, basically all the existing JavaScript infrastructure that we have. So GHCDS, that's a project, and it's, like I said, we compile Haskell to JavaScript, and the goal is to really stay close to GHC, since that's been tremendous help. Like we can pull source code from HaskellX, compile lots of packages, run their test suites, and if they work, then we get a great confidence boost that we actually are doing the right thing. So far, that's I think been worth the trouble of going a bit further to ensure compatibility. GHCDS uses GHC as a front end. It's a standalone program. You can install it with Cabal. I'll show how in the next slide. So GHC does parsing, type checking, desuring, and well, it gets to the optimization phase with core that Simon Peyton-Jones gave the keynote about. After core, the next step in the pipeline is the STG intermediate language, which is really close to core, but it has a bit more information for code generation. And it's a bit more messy. But that's what GHCDS takes. It takes this basically functional language and takes over from there on. It has its own binary format. It has its own linker. Like I said, the linker is similar to GHC with split objects. So if you have a program, the JavaScript file that you get is everything that you can potentially reach from your main action. If there's something in a module or some package that you use, but you don't use the whole library, then it won't include the parts that you aren't using, that it knows that you aren't using, since, well, you can't really see everything. But that's the basics. It's still not on HaskellX, but it's relatively easy to install as long as you have GHC 7.10.2. That comes with a Cabal version that's new enough to support GHCDS out of the box. You can install from HTTP just the latest snapshot from master. It takes a snapshot every day or every few hours. That's a completely prepared source distribution, so once it gets the green lights to go on HaskellX, this is exactly the file that's going to be on there. You need a few dependencies, a few libraries, see the README, but it's other than this, there's not much more to it. The stack program also has GHCDS support. That should be even easier, since it should take care of the dependencies, or at least warn you that something is missing. And if you have a stack YAML file with stack 1.6, I think is the first release that's going to support it, and that stack YAML file requires GHCDS, it will automatically install and boot GHCDS with this one command. By the way, the GHCDS boot thing is the program that builds all the libraries that come with GHCDS, and that includes the libraries like base, integer DMP, GHC prim, and also the included GHCDS base library for JavaScript interaction. And once you have the compiler, it really works like GHC. You just compile Haskell programs and you get a subdirectory with a few JavaScript files, an HTML file that you can load in the browser, and both the HTML file and the all.js file will start your Haskell program by running the main action. And if you do things like printing things to standard output, it will just do the same thing in Node.js, which makes it really easy to test Haskell programs with GHCDS on the command line. And if you build a package, then the one thing that you need to change over normal Cabal install is the --GHCDS option. The default compiler for Cabal is normally GHC, and well, this changes it to GHCDS. And most packages compile. Your GHCDS boot will build a whole bunch of packages already, including ASIN, text, byte string, I think binary. But if you have something that you think doesn't use any native code like C libraries, then you have a reasonably good chance that it works with GHCDS. So you can probably just try it out, and if it breaks, then probably file a bug report. Cabal support is also built in, Cabal 122, which comes with GHC 7.10. And if you have a project, you can, for example, set the default compiler for your project to GHCDS by creating a Cabal config file. And if you have a package description and you need specific handling for GHCDS, you can use the GHCDS implementation flag to check for the current GHCDS version. I should warn that GHCDS is treated as a derived compiler of GHC. It's for compatibility. GHC GHCDS has more or less the same features as GHC when it comes to the front end, things like GHC generics or type system extensions. Those are all provided by GHC. So if you really want to check that it's not GHCDS, then you have to check for or have to do this in the else clause here. But some things you don't need to do in conditional things, like JS sources is similar to C sources. If you have C sources for your Haskell program, GHC will just build them with the C compiler, include them in the library. And JS sources will, only for GHCDS, include JavaScript sources from your package in the library. Those will be included in the final JavaScript source blob for any program that depends on the package that you have there. So for those, it should be fairly straightforward to do those. Those are basically new things. And you have GHCDS options and a few other things. And there too, if you have GHC options and GHCDS options, your GHCDS options will be added to GHC options if you have both reachable. They won't override it because of the same derived compiler ID. So currently you have most Haskell features supported. We have, yes?
You mentioned that FFI stuff is hard to do with GHC.js, but your earlier examples will...
I have a heavily patched version of Gloss in my code. I'm going to push that to GitHub soon. Gloss does have sort of pluggable backend architecture, but there are a bit too many OpenGL assumptions baked in to really make a separate package to provide the GHCDS backend. So I had to hack it a bit, and it still needs to be cleaned up. But other than that, it's just a Gloss rendering backend that uses the JavaScript FFI to render to a canvas with the Canvas API rather than the OpenGL API. And that uses this Cabal implementation flag to select that backend if you use GHCDS to compile. So for the user, it looks exactly the same. But there's a different code paths selected in the backend, and the dependencies look different exactly because of this, these conditionals in the Cabal file. So it will depend on OpenGL. If you compile it with GHC, it will depend on GHCDS base, which provides the canvas bindings if you compile it with GHCDS. But it's unfinished, but I'll come back to the foreign function interface later. So what we do have is more or less complete support for all of Haskell, which includes concurrency, lightweight threads, software transactional memory, numeric types, and well, weak references. We have support for some sort of pointer emulation. If you pass the pointers or blobs of memory to foreign functions, there's a way to handle those things. It gets a bit hairy there, but it's possible to, if you add the right JavaScript code to support most existing packages, if you can at least provide an alternative for any foreign code that you have, which might be quite a bit of work. And we have two main targets. One, of course, that's the main reason for using JavaScript is the browser, but the other is Node.js, since it's really easy to use it for debugging, for working with the compiler, but also for automated testing. If you run Cabal test, then it will run the test suite of your program, of your package with Node.js in the background. It will just work much more nicely. And there are other things too, like if you have a custom build method for your Cabal package, then you have a setup HS file that needs to be compiled. GHCDS can't generate native code, but it can generate JavaScript code. It knows where Node.js is, so it wraps up the whole thing in a script that starts a Node.js interpreter and runs your whole Cabal setup script with Node.js. And for that, it needs to read files. It needs to read or write your setup config. It needs to query GHC package or GHCDS package. So it starts these things in the background. And all these things are just supported. You can use GHCDS to write cross-platform shell or system programming scripts as long as you have Node.js available on the target system. It's much better than using Bash or something, I think. More recent features are heap and CPO profiling. We have the same thing based on cost centers as GHC has. And the project I've been working on most of the time in the past 6, a bit more months, is a major rework of the GHCDS base library, which is the library that comes with GHCDS and does the basic interaction with JavaScript. It provides all the features for inspecting JavaScript values and some bindings for the for some common JavaScript APIs. And it used to be about 5 modules, and it's grown to about 70 modules, and it has support for many built-in JavaScript things like XML, HTTP request, Canvas, animation frames. I'll come back to those things later. The things that are currently in progress after this base library has been finished are the GHCDSI REPL. So it just really needs to be made more production ready to make more reliable, but the basic features are there, you can play with it. The new code generator is still a bit further out. That's the thing that's going to support more flexible code output, native tail calls, and also make hopefully compiler development a bit nicer for me. We still need tools like GHCmod, IDE backend and things. GHCDS is based on the GHC API, and it should be possible to modify the GHCmod and IDE backend tools by setting the GHC API up in the way that it reads the JavaScript target files and reads the correct package database, but there's still some work in that. It shouldn't be impossible since it's fairly close. So the new base library, I've been talking about improved base for a while. It used to be in a separate branch, a massive rewrite of this thing. A few weeks ago I merged it to the master branch. It's still not quite released, but it's already so much better than the old version. But we're still finalizing the API. There are many new bindings, like I mentioned, for XML HTTP request, for basically everything JavaScript supports. There's some binding for Haskell for it. Well, not quite everything, but a whole bunch. And also, this should be the place to look if you want to know how to interact with JavaScript. So there are new foreign function interface extensions that are used here, and it should be the best way to provide bindings for JavaScript. There's also a comprehensive JS string library, which is the same API as the text package. It tries to do actually correct Unicode handling with surrogate pairs and things that the text library also does. But JavaScript makes really hard since they are still stuck in the old 16-bit code points era, and so this tries to be a bit better. It also has Fusion. The GHC is hopefully going to be released on HackEdge fairly soon, but we still need to flesh out the last bits of this library. The GHCDSI, that's not in the master branch. You need to get the GHCDSI branch for that. And like I said earlier, it's based on the GHCGS code generator. It compiles JavaScript, so it doesn't use the GHCI bytecode linker. And the result is that we don't have debugging, stepping, tracing of Haskell code there. If there's real interest in that, then it might be added in the future, but so far it's probably going to be left out for a while. If you install it, you need the socket.io Node.js library. There are some basic instructions there, so play with it, but don't expect it to be quite ready. The profiling that I mentioned before is completely there. It's based on cost centers that are the same as in GHC-based Haskell code. And what's new since last year is time profiling. And that currently only works on Node.js. Since we use the Node.js statistical profiler, it takes a sample every millisecond of the current instruction pointer and the stack. And there's a library that records the current cost center in the call stack and a modified modified sample log analysis tool that reconstructs all the cost centers in your profiling report. So in the end, you get a profiling report that shows you the time spent in all Haskell function or in all Haskell cost centers, but also in the JavaScript functions beneath or above those cost centers. So you get this, both the JavaScript and the Haskell part, which is, I think, pretty neat. But unfortunately, it limits us to just Node.js at the moment. We need to instrument or change something in browsers to make this work, and they're all not very happy on adding native code or plugins to them. So they just make it very hard. And doing it from JavaScript itself, that is almost impossible to do it without biasing the sampling too much. So that's the status of the project. I mentioned the new code generator, but before I can say something more, go into more detail on that, I need to show how Haskell runs on the browser. So if you compile your Haskell program to JavaScript, there's one entry point, that's $run. $, is the prefix that GHCDS currently uses to make sure that it doesn't clash with too many existing JavaScript things. And this thing, which normally this your program when you just run the old JS file or load the index.js file that you get from compiling a program, it will run the main Haskell action. This thing returns immediately, and it starts your Haskell action in the background, and it will take over by rescheduling itself and running Haskell until it's complete. So if you, it's normal Haskell. So if you, well, print something like this, that's going to be the result. And let's see. But we can make it a bit more interesting, and we can prove that it actually does, since, well, my slides, I've written them in Markdown with Pandoc. And for all the Haskell source snippets, I can indicate that they're runnable, and have a preprocessor that extracts all the runnable code snippets, makes a module out of them, compiles those with GHCDS, inserts them back into the slides, and it runs them. So my dynamic text function is something that takes an HTML element on the same slides, function. Let's see, no, a start value, the thing that's fairly small in this text field, and a function that it applies to the value. So if I type in here, then it changes this. Oh, why doesn't this work? Yeah, I did, but I can't type letters. For some reason, my keyboard is broken. I can't type backspace, so you can see that something works. All right, so go to the next slide. Yeah, so I can do Haskell in this browser, so if I get bored, then I think I can still know why. Well, this is the Pong example from the Lens library, and it uses the gloss backend that I mentioned before and that I showed in JSI. And unfortunately, since my keyboard is somehow broken, I can't really win since I can't control my pedal, but normally I could. And that's really simple to write. If I have some time at the end, I'll show you the source code, but it will be on GitHub. So when we run Haskell through this Haskell run function, what Haskell does is, or what that run function does is it adds the thread to the run queue, it starts it up, and it makes sure that the main loop is running. The main loop is the main entry point from the Haskell code to where all the Haskell code is run from. And it picks work from a thread as long as it has work to do. It keeps running, calling into functions from the thread. The thread returns the next function to call, and after the time slice is up, then it will switch to the next thread, or otherwise it just keeps on running these things. So we have a main loop that controls all the threads, and all the threads themselves, they make sure that they don't stay busy too long in a single call. They return the next call to the main loop, and that gives the whole, makes the whole threading work. So we have lightweight threads on top of this main loop that controls them all. So does it work? Yeah, it works really well. So let me check if the next slide works. This slide just started 10,000 threads. It's created a table with all these table cells, all the threads. I think they sleep for a random number of milliseconds, then change the color of a single table cell that they're created for to a random new color, and then go to sleep again for a bit. If I switch away from this slide, but I won't for a minute, then it will kill them all again. I have to onActivate with cleanup function. That's just one of the utility functions in my slide program, that when I switch away from the slide, it runs an action. It has all the thread IDs collected, and it throws an async exception, a thread killed exception to these, and they all stop. So these things are gone in my next slide. They won't affect my next animations or make things go less smoothly. So 10,000 threads gone. So to make sure that these threads work, we have to make sure that we don't spend too much time in a single call, we have to return to the main loop fairly quickly. If we have something that's function f of an x and predicate, and the x is of maybe a, and we want to pattern match on the constructor, we have to force this thing. It has to be in weak at normal form before we know if it's nothing or if it's just. If we do it in the way in the JavaScript pseudocode that's sort of correct below, that might work, but the thing is the reduce call is a recursive call. So if this reduce call takes very long, then this thread would block the operation of other threads. So in GHCS we don't do this currently. We have something similar, but it looks a bit more hairy, but it's more or less the same thing if you squint a bit. It still reduces the thing, but it returns the result of that. And it makes sure that this call is in tail position. So instead of getting the results from the reduce, it pushes a continuation on the stack, which is the function f1. It pushes everything that it needs on the continuation, which is the predicate. It still needs p for whether it's just. Other than that, it just immediately returns to the main loop, and the next call will probably be another reduction. And the thing is, this allows us to be split up the whole evaluation in really short steps that make it possible to switch away from this thread. It adds some overhead, but it's still surprisingly fast, I think. But I do think that this is a bit inflexible. Like one of the things that you could see of the first version, this is a function of x and p. In the next version, since we do need to return to the main loop every iteration, we can't use normal function arguments anymore, since the main loop just calls the function without any arguments. So we use some global variables to pass these things. That's not ideal. And also this code is much longer than this code. And for some code, if you have a small JavaScript library or something where you know that you don't really need these preemptive threading, that's a cost that you might not want to pay. So the other big project that I've been working on is a new code generator that makes it easier and possible to, at link time, select what kind of program you want. And for that, we replaced the completely untyped AST in...
May I have your attention, please?
All right.
May I have your attention, please? The public
addresses these things by switching from the untyped current AST to a typed intermediate language. This makes a... and also we keep... let's see... yeah, so the explicitly typed AST, similar to what Simon Peyton-Jones in this talk about core mentioned, would hopefully save a few years of my life debugging compiler optimization problems. Since recently I haven't really done much work on the GHCDS optimizer, since it's just completely impossible to guarantee that you still do the correct thing if you have clever optimization rules. It's really frustrating that, especially now I can compile much of Hackage, I can always find something that breaks my clever optimization thing. So, but with types in the AST, you can say, hey, restrict your optimization rules based on the types of things. And well, we can also check if the things are still correct, if all the assumptions are still correct. And it also keeps the intermediate code, the non-tail calling, the non-CPS transform code of the first of these two slides around. So if you don't want fully threaded code, but you can, but you really need smaller outputs, and perhaps faster on some browser engines, JavaScript engines, you have that option. And there are a few other things like source maps. Those are part of GHC 710's source location annotations. And also primitive things that can be rendered at link time. For example, if we want to make ECMAScript 2015 tail calls, there's an option for that. But this is all not quite ready. This will take a few months before this is really done, but it's definitely on the radar, and this is the big project. I think I was planning to do this before GHCDSI, but the demand for GHCDSI was a bit too great. So how do you interact with JavaScript from the browser? There are two things where you really have this boundary. One is the foreign function interface, one is threading. And for a function interface, we have an extension to GHC that adds, that's called JavaScript FFI, which basically does the whole thing. That's new. We also support the C-call FFI with a compatibility wrapping thing. I'll give an example of that in a moment. And this is the low-level mechanism. There are higher-level things like GHC, JS, FFI, QQ, which is a quasi-quoter for a function interface that's a bit more convenient, and GHC, JS DOM, which is a program for a library for writing cross-platform programs. The quasi-quoter is really convenient. You can just write your JavaScript expression quasi-quoted. You backtick your JS or your Haskell expressions to or Haskell names to anti-quote them, and it will automatically marshal them through the type classes support by GHCS base. It's still relatively experimental, but this just generates through quasi-quoting and template Haskell the normal JavaScript form function interface things. GHCDS DOM is bindings for the whole DOM API generated from IDL specification. It has WebKit GTK and GHCDS backend, so the name is a bit not quite right. But the idea is that if you use this thing to talk to or manipulate your document, then you can compile a native application with the WebKit library with GHC. You get faster code, you get something, a native program, and if you compile it with GHCDS with exactly the same source code, you get a website or something that can be run in the browser at least. So, but everything in the end comes down to the foreign function interface. We have JavaScript and C-call. Both of these things work. In JavaScript, we have some extensions that I'll show in a second. The types that are allowed through FFI are basically the same as the ones in the C FFI. So you have all these ints, words, characters, 64-bit ints and 64-bit words. The last two are a bit different since JavaScript numbers are all floating point numbers, double precision. So you have 64-bit, but you need you don't have quite that. You only have 53 bits of precision. So what you get if you have a 64-bit, you get two function arguments. You get if you have something that you call with one 64-bit number, you get A and B, and one is the high least significant bit and most significant word. You can wrap them in some objects, but we don't do this through the foreign function interface. If you want this to be efficient, then you can write really efficient code that does really low-level manipulation on these things directly. And the other things, not all of these are directly possible through the FFI. Pointers and stable pointers are just like the C-call FFI, and those are also passed as two arguments, since JavaScript doesn't have pointers, but we can pass a typed array, something that has some resembles some region of memory, and we can pass a number to represent offset into that memory. So if you loop some pointer, you just bump the number and you keep the same memory region. That works reasonably well for supporting existing packages out of the box just by providing a JavaScript implementation of the C functions they tend to call. There's one thing that's new, and that's the JSRef type. That's only supported for the JavaScript FFI. That's basically the thing that you use in GHCDS to wrap any JavaScript value. Well, to give an example of the C-call FFI, if you have the text package that does things like passing pointers, primitive byte arrays, numbers, which are some C size, which is I think a wrapper for int32 or word32. You can write a JavaScript function for those. It's prefixed by $h again, and you just need to take into account that pointer is something that's represented by a typed array buffer and an offset. All the other things are, I think, size 1. Yes, so we have the dest pointer, which is the two things, then the source, which is the byte array, the offset and the length, which are these sizes. And that's what you do. You just operate on those things, and that's how the text package is supported. The same way the byte package is supported, byte string package is supported the same way. So there's no change in the Haskell source code. Just a few implementations of the C functions they do in JavaScript functions. The JavaScript FFI has a bit more functionality. You can actually write more complicated calls, and it has a placeholder syntax for arguments. So if we use the math.syn function, Then from double to double, we can use the $1, the first placeholder for the first argument. That should be reasonably. I can still not type. I can make it an invalid input again, but interesting. Well, if we have a 64-bit value, these placeholders change a bit in syntax. You get for the first argument an _1, _2 for the first and second half, but it's still fairly straightforward. These are still expressions. So this thing is a JavaScript expression that returns a bool, and those are automatically converted back to Haskell bools. We can also do statements. If we just add a semicolon, then we get the statement. We have the result placeholder, which is $R. So we can explicitly assign the result here, and this gives exactly the same result as the earlier one. We can make more complicated statements. We can do local variable declarations. The FFI code will make sure that it won't clash with anything else in your code. So this does a repeated sign application or something, and it's so any JavaScript expression that you can think of, or a JavaScript statement thing, should more or less work. It's inserted directly into the function, but it makes sure that all the variable names are unique. We do, and that's the last thing that I should note, have a difference between the safe, unsafe safety specifications of the thing. In GHC, JS, if you unsafely call a foreign function, then if any JavaScript exception happens in that function, the GHC runtime won't be able to do anything about it. It will propagate to the top level of the main loop. The thread that the function was called in will be dead, and that's it. It will be removed from all mvars or other things that it was blocked on, but it won't be able to handle the exception in the Haskell code. If you do it safely, the JavaScript exception is converted to a Haskell exception, and you can handle it the normal way. So this foreign call test first has something starting, and then it takes an action and a name. It first prints starting that action, and then prints finished when it gets to that point. And it catches any exception that action does. I think, let's see, I don't have the code that actually calls this thing, so I should have taken more care. Well, but I have two calls. One of them does the unsafe import, and one of them does the safe import. The unsafe thing only gets to the first line. Then it tries to run F, but there's an exception. The thread gets killed, so it's dead. The other one, the safe one, actually does make it to the exception handler of the fcatch e some exception. It's converted to some Haskell exception, and that's printed there. So that's the main difference between safe and unsafe in GHCGS. We could have used other names for that, but it seemed close enough to what they actually mean to reuse the existing names in the grammar. The other thing for the foreign function interface, the auto safety thing, that really does mean something different in GHCGS is interruptible. And in GHCGS, it still means interruptible, but it also means asynchronous. So if you have an interruptible FFI function, your thread, the thread that calls the FFI function, will be suspended until it gets woken up again, and that's done by the $C placeholder. If you call that thing with the result, the thread is woken up again and it continues. In the meantime, the thread is interruptible, so you can kill it, and you can it will receive the exception. And this is really useful for doing bindings for asynchronous things. For example, if you have an XML HTTP request that gets a callback, and the callback is the onload callback, which will be called when the result is in. If you do an interruptible FFI call for that, your Haskell thread will be suspended until this onload thing is done. Well, there should really be some error handling in there, of course, but look at the actual binding in the GHCDS base library, and it's much bigger, but it also handles all errors. And you can use the Haskell exception handling mechanism to do the rest of the work. Like if you use these XML HTTP requests thing to request some data, but you say, I'm going to time out this after a second, you can wrap this in the system timeout call, and it will send an async exception aborting the call, but you'd rather cancel the request. And this code just does that. It used the onException thing from control exception, and it will do the JS abort call when there's an exception that has aborted this call, then propagate the exception. So this automatically cleans up the after itself when it's interrupted. And the same thing, it was what made the gloss backend nicely remove its own canvas from the document.
Leave some time for questions.
Yes. Well, there are a few extensions like unbox tuples. But you have to enable some extensions for that. The other thing is threads. We have lightweight threads. Normal threads are background. But there's one main problem with those. If you call into Haskell, but your call into your Haskell runtime immediately returns, there are some situations where that doesn't really work well. And one of them is event handling. And here, this shows the main way of how you do event handling in GHCDS. You create a callback, a Haskell function that calls back into your Haskell runtime. You pass that to something, or you make sure that it gets attached as an event handler to on some element, and that thing will call it back. But the problem is if you have something like an on-click handler, and you want to stop propagation of the event, then you have to do that before the event handler returns. And there are a few more of these things, like if you have animations synchronized by request animation frame, you get a callback from the browser, and you better update everything you need to draw before you return from that call. So asynchronous threads aren't quite enough. So we do have another type of threads. Those are synchronous threads. Those don't get interleaved with other threads. We can't receive async exception with those, but the one downside they have is that they can't do blocking operations. So if you wait on an mvar or you do anything that's blocking, you stop. The problem is your JavaScript guarantees that you return some value before you return from the call. You can't guarantee that anymore. So there are two ways of starting synchronous threads, and those have to do with how you handle blocking operations in your thread. One of them is, if you do a blocking operation, is receive an exception that says I'm blocking, and you can handle the exception as any other Haskell exception. It looks like an async exception that you can't mask. Since if you could mask it, there's nothing you could do. You destroy those guarantees. The other one is continue async. So you make sure you do your important things that really need to be done before returning first, and then, well, you don't care if you do a blocking call, you just continue as a normal thread afterwards. So this is an example. Threads work together as the DHCD, this uses the gloss backend. You have a bunch of asynchronous threads that update IO refs that have each their own position of some disk. And there's another synchronous thread that is run by Gloss, the Gloss main loop that's run by the request animation frame loop. So the repainting is all done synchronously, everything else is asynchronously, and normally I haven't really run into trouble combining these threads. You just have to know what you need to use where, and you have to be a bit careful that you don't do blocking operations in the asynchronous threads. That's more or less what I wanted to say. This is the implementation of the main loop, but it's all rather unfinished. So I will be at the hackathon. The Haskell or the GHCDS base library is still not quite finished. So if anyone wants to have a look at the API, then please talk to me. And well, there's also lots of help we can need for well, better testing and binary builds and stuff. So well, is there time for one question?
Yeah, thank you.
First of all, amazing work, thank you. But have you thought about using web workers for real threads? I don't know if it's feasible for that.
They are usable, but the problem is you don't have shared memory. Well, one feature of the design of GHCDS is that the whole Haskell heap is completely visible. So we don't use JavaScript closures. All Haskell objects are normal JavaScript objects. So what we can do is if you say I'm going to run this IO action in a web worker, copy all the data referenced by this IO action, make sure that you have everything it needs on that web worker, and then run it there. But it's a bit tricky. Doing normal lightweight threading on these things without shared memory, no, that's not really worth the trouble. The same reason for that, the same reason there's no parallelism. So the par annotation, it just gets ignored by GHCDS since there's really only one thread that you can really use. So it's too heavyweight. That's the one thing. But it's usable if you really want to use it as something, as a separate process. Fortunately, we don't have a good way to detect the symbols that you need yet. We could add some heuristics, but usually the program will fail with an undefined symbol exception when the code tries to call the non-existing C function. So this text library has a few C functions, and you usually see fairly quickly where it breaks. But yeah, there's no automated way yet, unfortunately, to catch this.
I just read that there's a C or C++ to JavaScript.
Yes.
Could that be used somehow to run this kind of code?
Yeah, but you'd have to use mscripten, or usually it takes a while to really make it work. If you have a big C library that you want bindings for, then you can definitely use this. But there's a small layer to manually glue everything together correctly. But it's definitely doable.
The output file sizes for GHCJS have been coming down. Is that going to continue? Do you think there are more optimizations to be got on output size?
Well, the new code generator, I hope that this will really improve code size by 50% or more. But the thing is, currently there's lots of duplication. Many patterns are repeated over and over again. But I don't really like adding optimization rules for catching these common things, since I don't have a good way to find mistakes in my current AST. I can't find any preconditions that are going wrong, and I always find bugs. So I've been really conservative in adding these things. And once this new thing is really in place, then I'm going to add more. And I think there's also lots of work that can still be done in tweaking optimization options and some parts of the base library. If you have standard output, it needs a whole UTF-8 compiler, which is fairly heavy. Those can relatively easily be stripped by just some customization of the compile paths. So it should be going down slowly, but it hasn't been a priority for a while. So I just wanted to make the infrastructure and the base library correct, since getting the size down is something that's basically a free thing. When you use it, then yeah, you don't have to change anything for it. And so I preferred having the APIs and the libraries first, since those require more discussion and probably more change from users.
Would you consider a WebAssembly target, or is that completely out of the question? Because I think that would solve a few of the problems which people are referring to, like the footprint size and that kind of stuff.
I would consider it, but the current specification is really limited. And it would require a rewrite of much of at least the storage manager. So currently, GHCDS maps Haskell heap objects, all lifted things are wrapped in something that if you call it, it will reduce it to weak at normal form. And there are some properties. If something is a data constructor, you have some way to get the value out of it. Just, for example, they are all JavaScript objects. You can't use objects in WebAssembly. You all have this flat typed array memory thing. And the new code generator makes it a bit easier to target these things, but it still requires a bit too much work to actually consider it. So I'm hoping that if they relax the specification, I'm hoping that there will be a sort of binary distribution for existing JavaScript, not just a subset. Then we can immediately skip this parsing step and make loading the code a bit lighter and make it a bit more compact. But if it really has to be this target that's only, well, easy to target LLVM or really low-level code at, yeah, then at the moment it's just a bit too much work to focus on, I think.
Okay, I think we should stop here. Let me very briefly explain the rest of the program. There's going to be drinks downstairs. There's going to be